Okay, welcome to Lesson 3 of Module 7. In this lesson, we're going to talk more about square roots, and we're going to talk about cube roots, which we haven't done yet. One of the things that we want to establish or want to know is just that for any positive number, there exists a square root, and there also exists a cube root. Which you can probably figure out what a cube root is. We'll get into it in a minute. But they exist, and not only that, there's only one, for any given number, there's a unique or only one square root. And the reason that that's important, that might seem like a duh, that's obvious, it's not necessarily obvious, and the reason it's important is because if you're going to be solving equations involving squares and square roots and cube roots, then you're going to need to know that such a number exists, and that when it does exist, it's the only one, or it's unique. So that's what we're doing in this lesson. So we're going to open with a little activity called Find the Rule. So there's Find the Rule Part 1 and Find the Rule Part 2. And so let's read what it says here. It says that the numbers in each column are related. Your goal is to determine how they are related, determine which numbers belong in the blank parts of the columns, and write an explanation for how you know the numbers belong there. So I'm going to let you work on that. You should pause the video and see if you can find the rule in the first table, and then it will be a different rule in the second table. Okay, so I'm going to begin just filling in numbers for Find the Rule Part 1. So, and you can check your answers against the ones that you got. Okay, you might not have known quite what to write here or here. Okay, so how'd you do? So the rule for Find the Rule Part 1 is something like, to find the number in the second column, I squared the number in the first column. So 2 squared is 4, 3 squared is 9, and so on. So I took this number, squared it, and got that number. But if I already knew this number, like in this case, you know, say this is a number, another way to state the rule would be to say, to find the numbers in the first column, I took the square root of the number in the second column. So the square root of 81 is 9. And the square root of 169 is 13, and so on, okay? And then down here, we wrote it with variables. So I have m in the left column, so m squared would be using the rule to find the number in the second column. And then here I knew n was the squared number, so square root of n is what would go in the first column. Okay, so think about that for a while. If that's confusing, maybe just give yourself a couple minutes to kind of take it in before we go on to Find the Rule Part 2. Okay, so for Find the Rule Part 2, I'm going to start filling in the blank spots that you should have had. And love those multiples of 11, right? Let's see, 64 would be 4 over here. So 10 would be 1,000. 7. Ooh, 2,744. Well, I know it's got to be bigger than 11 because that's 1331. So here's a case where you just got to start trying some stuff, right? So 14 fits the rule for that. And then I'll leave the 2 for just a minute, the other 2. So for this second one, your explanation for this one could be something like, to find, given a number in the first column, I take the cube of the number, or I multiply the number by itself 3 times, use it as a factor 3 times, whatever, to get the number in the third column. So 2 times 2 times 2 is 8. 1 times 1 times 1 is 1 also. 3 times 3 times 3, or 3 cubed, is 27, and so on. So that's going to work for all of these. Notice they're getting big really quickly with the cubing. So if the number is p, then for the second column, for find the rule part 2, I would write p to the third power, or p cubed, because I'm using p as a factor 3 times, p times p times p. Okay, but what about if I'm given q? If I'm given q, I need to know what number can I multiply by itself 3 times to get q. Okay, and we have a special notation for that, and it looks just like the square root, and I'm going to put, of q, except that we put a little 3 here. So that means cube root of q. So if I'm given the number, such as, maybe it's 64, 27, I have to find out what number multiplied by itself 3 times is going to give me that number. And so that would be the cube root. So I could say the cube root of 64 is equal to 4. Cube root of 64 is equal to 4. So remember over here, let me go back to this color. Over here, I'm going to say something like the square root of 81 is equal to 9. So we, you could think, well, why don't I put a 2 there? It's just, it's assumed that it's, need room. The 2 doesn't need to be there because we just assume it, okay? So it doesn't belong. But so that is the square root symbol. Over here with the 3 is the cube root symbol. Okay, so that's some new notation for you in this lesson. Okay, so as you were filling out these tables, you probably noticed, or you could think, there's only one number that would be the correct number to go in any one of these blanks. So for instance, for this blank right here, I have 49. The square root of 49 is 7. 7 is the only number that I can multiply by itself to get 49. So 7 is the unique square root of 49. So that's that idea of uniqueness. There is not another number that would work to be the square root of 49. And likewise, there's not another number here that could be the square of 10. 100 is that number. So it's unique, and also there were no blanks on our chart. Okay, so we could always find that number. Sometimes it was more difficult than other times, but there does exist a number, and once you find the number that exists for these cube roots and square roots, it's unique. It's the only one that would work. Now we've used in this chart, you notice these are all perfect squares here, And these are all what you would call perfect cubes, in the same way that these are, that they have an integer root. So 216 is a perfect cube because 6 times 6 times 6 is equal to it. Okay, but we could extend these tables until they included just an infinite number of rows. We don't have to have whole numbers that we take cube roots of. They can be decimal numbers. They could be fractions. They could be lots of different numbers. So we could have an infinite number of rows in this table, but yet every time there would be an exact square and an exact square root that went with it. So, and cube root also. Okay, so again, like I said in the opening, the reason this is important is because we're going to be solving equations with square numbers, squares and cubes and variables with those, and we need to know how the properties of equality work for that. So remember, properties of equality are this type of thing. Like if I have, x plus 3 is equal to -10, I know that I can add 3 to both sides of that equation and get a new, I don't want to add though, do I? Sorry. I would like to subtract 3. Of course, I could add 3, but it's not going to help me solve that equation, which is what I wanted to do. I'm going to subtract 3 from both sides of that equation, and I will end up with a new equation that has the same solutions, and I can get x by itself and get a value for that variable that works. So -10 minus 3 would be -13. And so x equals -13 works in there. So I used the subtraction property of equality, which says if I subtract the same number from both sides of an equation, if I subtract the same number from both sides of the equation, I will still have a balanced equation. I'll have another equation, new equation. My new equation, x equals -13, has the same solution as the original equation. Okay, so that's the properties of equality, and we know that we can do that with addition, subtraction, we can do it with multiplication, and we can do it with division. So we can do it with all the operations, and we use those to solve equations. All right, so let's look at this equation. This is a really simple equation that I think you can tell is true right off the bat. So that's a true equation. 25 equals 25. And what happens if I take the square root of both sides of that equation? So let me get a different color. I'm going to take the square root of both sides, and I'm going to get a new equation, right? New equation that says 5 is equal to 5. So did that work? Do I still have a true equation? Well, yeah, I do. 5 equals 5 is a true number sentence, just like 25 equals 25 is. So what that's showing me is that if I have an equation, I can take the square root of both sides and come up with another true equation, an equivalent equation. So that's important. I could do the same thing with this equation. What about this one? 27 equals 27. Now this time I could take the square root, but I'm going to take the cube root of both sides. Can I do that? Does that work for my properties of equality? Well, yeah, it does, because now the cube root of 27 is 3, and the cube root of 27 over here is also 3. Okay, so the properties of equalities work. This would allow us to solve certain equations. Okay, so we have already seen where these types of equations come up. So when we were solving for the missing, a missing side length on a triangle, for instance, you know, this could be something here, we'd come up with something like x squared equals 81. And we would know then that since the square of that side length is 81, then we would know that we could figure out that x would have to equal 9. X would have a length of 9. And so, because we know that 9 times 9 is 81. So this is an example of an equation involving a square or squared variable. Now, there's another number that would work in that equation, right? It would be x equals -9, because -9 times -9 is equal to positive 81 also. So -9 would work, but we know that -9 can't be a side length of a triangle. So we're not going to use that, that solution to this equation because it doesn't make sense for our situation. So we're going to use the positive one. So just a reminder that we're going to be talking pretty much only about positive square roots in these lessons. You'll be doing a lot more with negative square roots when you get to Math 1. And also remember how this sign, square root of a number, always refers to the positive square root. There are 2 square roots for every number, one positive and one negative. But this radical sign right here is the positive square root. So it's just assumed. Same thing with the cube root, although it would have to be. So that's a little bit different situation. But at any rate, we're going to begin solving equations that require roots. All right, so let me get a clean slate here. Okay, so when we solve these equations, so here's a real simple one. So it's the same one we were just talking about. X squared equals 81. And I'd really like you to follow these steps because even though we've already figured out what numbers could be the solution, the steps that we're going to take are important for you for in the future. Okay, so just trust me on this. So what I want to do is I'm going to take the square root of both sides of this equation. The square root of x squared is equal to the square root of 81. So that's really what I'm doing when I solve an equation with a square in it like this. I can take the square root of both sides because we just showed that that's going to, it's the property of equality for that will hold. And so the square root of x squared is x because it's the number that I multiply by itself to get the number that's under the radical. So x times x is x squared. So the square root of x squared is x, and the square root of 81 is 9. All right, so I just simplified both sides. Okay, let's look at another example. What if I had x squared is equal to 81 to the negative 1. All right, how am I going to solve an equation like that? Okay, we haven't been doing much with negative exponents, but let's simplify that negative exponent. So I know that 81 to the negative 1 is 1 over 81 to the first power. So remember that, I don't have to write that, but the negative exponent is the reciprocal of that number. So 1 over 81. And so now I have x squared equals 1 divided by 81. So now I want to take the square root. Square root of x squared is equal to the square root of 1 over 81. Okay, and the square root of x squared is, once again, x. And now I have to figure out the square root of 1 over 81. So it would be the number that I multiply by itself to get 1 over 81. So 1/9 times 1/9 is equal to 1 over 81. So the square root of 1 over 81 is 1/9. Okay, and this is the double check right here. Okay. Okay, one more. What about this? We get x cubed is equal to 8. What is the value of x? Well, we're going to do the same thing we did with square roots, but we're going to take the cube root of x cubed, because that's going to give us x. So if I'm going to do that, I've got to take the cube root of 8. The cube root of x cubed is just x, because that's x times x times x is x cubed. And the cube root of 8 is 2, because 2 times 2 times 2 is 8. Okay, so the same property of equality holds for taking the cube root of both sides of an equation. One more thing, this symbol is called a radical. And these are radical equations. So, yeah, you can tell everybody you're working on radical equations. If I put, we said if we put a 3 here, that's the cube root, but it works for any number. So I can put an n there. It's the nth root of whatever number I have. We're only going to be working with square roots and cube roots for now, but you will get to in later math classes where you work with nth roots. So, but it's the same symbol. So the only one where we don't have to write a number on it is the square root. Okay, that's kind of the main one. All right, so let's move on to some exercises. You can work on exercises 1 through 9. Use a calculator to check your answers. And make sure you know how to find the square root with your calculator. We talked about doing that in the last lesson. But if you still haven't figured that out, you should get out the manual or get somebody to show you how. Okay, so go ahead and pause the video and work on exercises 1 through 9, then come back and we'll quickly go through them together. Okay, once again, the steps that you're being asked to go through to solve these exercises might seem a little bit obvious or unnecessary, but we're getting used to the math behind what you're doing. So when we solved x squared equals 169 before, we were using mental math. We were just asking ourselves what number could go into that equation to make it true. But we weren't really using properties of equality and steps to solve those. So these are very simple. You will do more complicated ones later, I promise. So, but we need to know what the principle is behind what we're doing. So that's why we're going through this. So just bear with me. Explain the first step in solving this equation. The first step, we want to get x by itself. So in order to do that, we need to take the square root of both sides, because x is squared. So so the undoing of that is to take the square root. Okay, remember if we used addition to undo subtraction and subtraction to undo addition and so on. Take the square root of both sides. Okay, that's using that property of equality. Okay, solve the equation and check your answer. So to take the square root of both sides, we're going to say the square root of x squared is equal to the square root of 169. Square root of x squared is x, and the square root of 169 is 13. So x is equal to 13. and check your answer. I'm going to check it by putting it back in the original equation. 13 squared is equal to 169, and it is. 13 times 13 is 169. All right. What positive value of x makes the following equation true? X squared equals 64. Whoops, that's not number 2. Sorry. I missed a page. 1 second. Okay, number 2. A square-shaped park has an area of 324 feet squared, or square feet. What are the dimensions of the park? Well, the dimensions of the park, there's only one dimension for a square. Well, there's 2, but they're the same, right? So we just need to find that side length. So we could say, well, let's call it S. We could say S squared is equal to, because I know the area is going to be S times S, is equal to 324. Right, and solve that equation. So to solve that equation, I'm going to say the square root of S squared is equal to the square root of 324. Square root of S squared is S. The square root of 324 is 18. So the dimensions are 18 feet by 18 feet. That's the dimensions of that park. All right. Here's an equation. 625 equals x squared. I'm still going to take the square root of both sides of that equation. Square root of 625 is 25, I believe, isn't it? And the square root of x squared is x. So x equals 25 is the solution to that, and I can check it by putting it in here. 625 is equal to 25 squared, and it does. Okay, number 4. A cube has a volume of 27 cubic inches. What is the measure of one of its sides? So, you know, we've got a cube here, and it's got 3 dimensions, and they're all the same. So we got S, and the height and the depth there. S times S times S. So to write and solve that equation, we've got S cubed is equal to 27. So to solve this one, we need to take the cube root of both sides, the cube root of 27. So the cube root of S cubed is S, and the cube root of 27 is 3. So the side length is inches, so it's 3 inches. Okay, now we're on number 5. So what positive value of x makes the following equation true? X squared equals 64. Well, I want to just solve this equation, so I'm going to take the square root of both sides. Square root of x squared is equal to the square root of 64. Square root of x squared is x. Square root of 64 is 8. For the explanation on this one, it's really just writing in words what we've been doing. So if you can explain that we're taking the square root of both sides, and we're going to use the positive square root of 64 for that equation, because -8 would also work, but we're asked what positive value of x makes the equation true. Same thing for this next problem. What positive value of x makes the following equation true? X cubed equals 64. Well, to do this one, I've got to take the cube root of x cubed to get, because I want to know what x to the first power is. And I'm going to take the cube root of both sides of that equation. Okay, so the cube root of x cubed, and everything I'm saying here should go in your explanation. I'm not going to write it out for you. The cube root of x cubed is x, and the cube root of 64 is 4, because 4 times 4 times 4 is equal to 64. So x equals 4 is a solution to that equation, and is a positive value of x that makes that true. But would negative 4 work in that equation? Would negative 4 even be a solution to that equation? And hopefully you'll see that it's not, because negative 4 cubed would be this, which would be negative 64. So it would not be a solution to that equation at all. Okay, got another one down here. So find the positive value of x that makes this equation true. So we have x squared equals 256 to the negative 1. So I'm going to, as my first step, rewrite this equation. X squared is equal to 1 over 256. You might need to review negative exponents as you do this lesson. You could look up that information back in Module 1, I believe. Okay. All right, so I want x to the first power, so I'm going to take the square root of both sides of this equation. So the square root of x squared is x, and the square root of 1 over 256 is, I'm going to have to figure out. And I know that 16 times 16 is 256. So if I think about it this way, if I multiply those two fractions together, I'm going to get 1 over 256. So the square root of 1 over 256 is 1/16. And that is the positive value for x that makes that equation true. All right, now find the positive value for x that makes this equation true. X cubed equals 343 to the negative 1. Okay, so I'm going to start by taking the cube root of both sides of that equation. Cube root of x cubed is equal to the cube root of 343 to the negative first power. Okay, so I did this a little bit differently. I'm taking the cube root right off the bat. This is an x cubed right here, isn't it? Cube root of x cubed is equal to the cube root of 343 to the negative 1. So that's my property of equality. I can take the cube root of both sides of an equation, and the cube root of x cubed is x, because x is the number that I multiply by itself 3 times to get x cubed. All right, and the cube root of that, I'm going to rewrite. I'm going to write as the cube root of the fraction 1 over 343. And you might remember from our table, I think this was on our table, that 7, I know that 7 times 7 times 7 is 343. So the cube root of 1 over 343 which is equal to x is equal to 1/7. So that's the positive value for x that makes this equation true. You could also write 1/7 as 7 to the negative 1. So either of those would be correct. 7 to the negative 1. Okay, so what I'd like to do now is take you through, just as a review of negative exponents, let's check that solution right there, x equals 7 to the negative 1. Is that a solution to our equation, x cubed equals 343 to the negative 1? So I'm going to take and put our solution in. So I'm going to have 7 to the negative 1 cubed, and I'm asking myself, question mark, is that equal to 343 to the negative 1? So what I've done, look at my arrow, what I've done is I've taken 7 to the negative 1 and put it in here for x. So 7 to the negative 1 cubed, that's x cubed, is that equal to 343 to the negative 1? Okay, and I'm doing this because you're going to see this in your problem set answer key, and also because it's a good way to review our exponent rules. So 7 to the negative 1 to the third power, remember when we have a power to a power, so 7 to the negative 1 is a power to a power, the exponents get multiplied. So this becomes 7 to the negative 3. Negative 1 times 3 is negative 3. And I'm still asking myself, is that 343 to the negative 1? Well, 7 to the negative 3 is 1 over 7 to the third power, to the positive third power. Still, is that 343 to the negative 1? And there's a number of ways you could go through these steps. It's just kind of fun to play with these exponent rules because you find out that they work, which is kind of cool. So 7 cubed is 343, so that becomes 1 over 343, and that's the definition, right? So now I can write this 1 over 343 is 343 to the negative 1, which is the same as that. Now, there are much simpler ways to check, but this makes use of our rules of exponents and is a good way to review them and convince ourselves that they work. All right, last but not least, number 9. In this one, we're not asked to solve this equation because you don't actually have all the tools to solve an equation like this, but you're asked, is 6 a solution to the equation x squared minus 4 equals 5x? Explain why or why not. Well, to know if 6 is a solution to that equation, all I have to do is put 6 in for x. So I can say 6 squared minus 4, and I'm saying, is that equal to 5 times x, which is 6. 6 squared minus 4, is that equal to 5 times 6? So 6 squared is 36 minus 4, and this is 30. 5 times 6 is 30, so this is 32, which is not equal to 30. So the answer to that would be no. 6 is not a solution to that equation because it doesn't make it true. Doesn't lead to a true statement. Okay, so we've been introduced to the symbol for cube root, and so we know that this is a radical. We call this a radical, and when we put a number here, n, we know it is the nth root. So if there's a 3 there, it's the cube root. If it's a 4 there, it's the 4th root. If there's no number there, right here it says it represents the positive square root if there's no number there. You know, here it says technically we could put a 2 there, but we don't. So, and the other thing we've shown is that the square or cube root of a positive number exists, and that's any positive number. It doesn't have to be a whole number. Any number, the square or cube root exists, and there can only be one. It's unique. So that existence and uniqueness we showed. Okay, I think you'll find this problem set fairly straightforward, but I'd like you to take care to follow the steps to solving an equation using that step of taking the square root of each side or the cube root of each side. Okay, but it should go pretty quick for you.